In this video, we're going to take a look at two more of the case studies. So we will look at questions 21 and 22. These two are nice because one is significant and one is non-significant. Okay, so remember the first thing you do is you want to figure out which variable is the dependent and which variable is the independent variable. All right, so looking at question 21 here, the way I interpreted this is that accidents is let's see, now I'm already forgetting what I did because it's such a confusing question. Accidents is the dependent variable and choose is the independent variable. Let me see if that's the way I've got everything. Yes, that's the way I've set everything up. Now, it's not particularly obvious the way Lane has written this particular question, and you have to kind of go back and read the experiment carefully. Since he's only asking for a correlation coefficient, you don't really need to worry too much about it. But at any rate, let's take a look. So treating those that way to where choose is the independent variable and accidents is the dependent variable, this is how you would work it, okay? So again, we would select the two columns that we need, and if accident is the independent variable, it has to go in the second column and passed, and this has to go in the first column and passed. Okay, so here we have choose as the independent variable and accident as the dependent variable. Now we select the two columns. We hit model, linear, bivariate. Okay, so there's a graph of the data. It looks pretty bizarre. And if you switch these axes, it still looks pretty weird. All right, but you can see this has sort of a negative slope. All right, and so let's see what the statistics are. If the slope is negative, the correlation coefficient is going to be negative as well. So in other words, you can kind of look at the relationship here as choose increases, accident decreases. Okay, so that's one way to put it. All right. However, let's see if it's significant. All right, so we would take this data, I put it over here so we can see it a little better. All right, so notice the correlation coefficient is negative, meaning as one of these variables goes down, the other one goes up. All right. Is it significant though? No. Look at the probability. It's greater than 5%. So what is the conclusion? The conclusion would be we did not find a correlation between accident and choose. All right. So again, you would normally put this in plain English, but since this is kind of a long story, I just shortened it for this example. Here's something you cannot say. You cannot say there is no correlation. There may be, we just may not have enough data to prove it. Remember, if you said that, then you would be accepting the null hypothesis. You also cannot say accidents cannot be predicted by choosing. You can't say that either. You have to be very careful not to accept the null hypothesis. All right? Let's see. So I did run tests of all the assumptions. You've seen how to do that in a previous video, so I'm not going to do it again. For this one, it satisfies all the assumptions. Okay, so let's take a look at question 22. So 22 asks for a lot more things, so we'll take a closer look at it. All right, 22. Use linear regression to predict how often someone rides public transportation in inclement weather. So they're going to respond to something based on this. From what percentage of accidents that person thinks occurs. So in other words, he thinks a certain number of accidents are going to occur, and then we're going to see how often he runs public transportation. So this is the independent variable. This is the dependent variable. All right. Again, we'll need to put all this into past. So I'll just do a new one for this so you guys can see how to do that. All right. So this time we want accident as the independent variable. Select columns. I think. Let me make sure. Did I do that right? Oh, God. Hold on. Something happened here. Okay. Let's see. Use linear regression if someone rides public transportation from the percent. Yeah, so accident should be the independent variable. Okay, now we need public transportation is the dependent variable. Again, remember, you have to put it in the correct way. Otherwise, you're going to get the wrong results. All right, so let's see. Model linear bivariate. So there's the relationship. As you can see, these two variables are positively correlated with one another. So depending on how often somebody believes accidents occur, they're more likely to, use public transportation. Kind of makes sense. All right. So I've taken these statistics here and pasted them into Excel so we can see them a little better. All right, let's come down here to the question. Okay. So here's the, let's see, so this is what we were doing. All right, so here we have all the results of this. All right, notice I've actually selected or added a couple of things here. So here's the slope, here's the intercept, here's the test of whether this is significant or not. Turns out it is, so we have a low probability. So this would be the conclusion. Public transportation increases with accident. How often somebody believes an accident will occur. And then you put the t-statistic and the probability in parentheses. Notice we don't say this is significant. We don't use the word significant. We say the direction of the effect. They both are increasing because it's a positive correlation. Okay, so let's take a look at the assumptions because this violates a lot of assumptions. So this will give us a chance to see how we deal with that. All right. Remember, in past, what we do is we click the residuals tab to get the assumptions. And the first one, the Durbin-Watson statistic, this is the test of linearity. It has a probability of 44%, so we've satisfied that assumption, but we've violated homoscedasticity. And when you copy this and look at the residuals, all right, univariate normality test, we've also violated the residuals. Okay, so how do you report that? Let's take a look here. The data are heteroscedastic. Notice that, or you can say the variance is not homogeneous along the regression line if you want. The data are heteroscedastic. So we accept the alternate when we have a low probability. Here's the BP statistic, Bruce-Pagan statistic, and the probability there. We've also found that the residuals are not normal. And that's what you say. The residuals are not normal. Not some BS like, we have violated an assumption. I don't want to hear that. I want to hear what the alternate hypothesis is. So here we have the statistic and the probability. All right. And then as far as linearity goes, remember we satisfied that. So we satisfied the assumption of linearity. In parentheses, you could put the Durbin-Watson statistic and probability, which I've left off of here. Okay, so that's how you do question 22. All right. So that concludes this video.